Hey everyone, meet MIT's Shawn Wang. Shawn studies Earth's climate and how it affects all of us. Let's go meet him.
Thank you so much, Fatima. I'm so excited to be here. And thank you all to MIT Abstracts and Not Anglia for having me for this presentation today. So today I'll be talking about wind and why it's an important part of the climate system and why I think we should all be paying attention to it. So first off, a little bit about myself. I'm a graduate student like Fatima at MIT. I love climate science, but I also enjoy skiing. I love hiking and I love reading as well. Here are some pictures of me doing those activities with my poster at a conference last year, with some friends skiing in New Hampshire, hiking Mount Rainier in Washington, as well as some of the most recent books that I've been reading. And so today I'll be talking about the climate system and climate science. And so what is climate science? It's a pretty complicated field with a lot of moving parts. Climate science involves studying the atmosphere, the oceans, the land, and how all these different components interact. Today, what I'll be talking about is my research, which focuses on just one aspect of the climate system, which mainly focuses on the oceans and the atmosphere and how they interact with each other. So first, I'd like to talk about how I got into climate science and how I became a grad student here at MIT. So I was born in southern China and moved to the United States when I was around 6 years old. And I moved to a small state called Alabama in the South. And I didn't grow up near any tall mountains or oceans or anything. So my experience with the earth and climate actually came through activities after school. In fact, during middle school and high school, I get involved in after-school activities such as Science Olympiad and Science Bowl, and these were activities that were pivotal in inspiring me to become excited about the climate system. So here are some pictures of me and my friends way back in middle school years ago, where we won a competition at regionals. And here's another picture of us in Washington, D.C. at the Science Bowl tournaments. So a lot of you might have heard the word climate thrown around and think that it's related to weather and might be wondering what's the difference between climate and weather. And so I'd like to provide a explanation first. So let's take, for example, Lake Spalding, California, which is shown in this picture here. When we think about weather, we might think about something like the forecast that we see when we type in the weather app on our phones or on a website, looking at how the rain will look the next day or the temperature and things like that. So weather deals with what happens in the climate system and in the atmosphere on the timescale of days to weeks. But when we think about climate, we're thinking about much longer changes across multiple years or sometimes even longer. Here is a graph that shows the changes in rainfall in the Lake Spalding area over the last 20 to 30 years. So you can see in the 1980s, we had a lot of rain that suddenly dipped down in the late 1980s and into the 90s and increased again and back down. And so the time scales and the changes that we're observing when we talk about climate are much longer than the ones when we're talking about weather. An important aspect that climate scientists are focused on that you might be hearing about in the news a lot is global warming and climate change. And this is one of the biggest challenges that we're facing as a society today. So for those of you that aren't familiar, global warming corresponds to the rise in global temperatures that we've been experiencing over the past few decades. This here is a graph showing global temperatures, so temperatures over the entire planet on Earth, and how that's changed over the last 200 years or so. So you can see that starting around the late 1900s, temperatures over the Earth began increasing a lot. And this is where we are today. And you might think, well, you know, a few degrees change in temperature might not make that big of a difference to you and I. We might, you know, not wear as many coats outside in the winter or might be a little warmer for us, but it has a big impact on ecosystems throughout our planet. For example, did you know that, like us, fish actually have preferences for different temperatures of the water? Some fish prefer temperatures around 70 degrees Fahrenheit, and some prefer ones around 50 degrees Fahrenheit. When we warm the planet and warm the ocean, that actually changes the environments that the fish like to live in, and that will change and impact the fisheries that we depend on. Additionally, not only do animals become affected by climate change, but plants do as well. For example, crops also like to grow in certain temperatures. And if we increase the temperatures too much, then this will make it harder for them to grow. So we've talked about rainfall and we've talked about temperatures, but the big aspect that I want to talk about today is winds and how that can also change in our climate. So we normally might think about winds as grass blowing outside on a windy day, or sometimes we might see some of these wind turbines spinning when we're outside. But the crazy thing is that wind can actually change on even larger scales as well. So this right here is an animation of wind fields over the Pacific Ocean. So you can see on the right-hand side is North America and South America. Right over here is where Fatima and I currently live in Boston, Massachusetts. And what you can see with the colors and the individual lines are the wind patterns themselves. And so there's a lot of structure and a lot of cool patterns that you can see. For example, up around here in North America, you have the jet stream meandering along. You have these cyclones that you can also see, these individual vortices. And the main topic that I'm focused on are what's happening here in the Pacific Ocean. So if we can play it one more time, you can start to see that these are actually the trade winds. So they're moving from east to west at all times. So the trade winds are really important. They're the winds over the Pacific Ocean that blow from east to west, like I showed in the animation before. And what that does is that actually makes the Pacific Ocean cool in the eastern part of the basin off the coast of South America and warm on the western part of the basin off the coast of Southeast Asia and the Philippines. And these trade winds are really important, and we've actually known about them for a long time. In fact, they're called trade winds because sailors actually use them to traverse across these oceans to trade back in the day. Sometimes, though, these trade winds can actually weaken or, in some cases, even reverse. And when that happens, the winds that blow the waters from the east to west that cool the waters here will actually reverse and make the waters in the eastern part of the Pacific warmer and the western part actually cooler. Here is an animation showing that feature where across the trade winds weakening, we can see the waters over the eastern Pacific Ocean getting warmer and warmer. So you can see that red patch developing really big, and that's sort of the trade winds weakening and the effect of winds on temperatures in the ocean. And again, you can sort of see that animation looped over. It's really cool to see just how dynamic our climate system really is. So there's actually a name for this feature that we're seeing when the trade winds weaken. It's called El Nino. And El Nino can not only affect the temperatures over the Pacific Ocean, but also climate throughout our entire world. This is a schematic that shows really what happens during an El Nino event. So you can see that we would expect the waters over the Pacific Ocean to get wetter, regions of Southeast Asia and Australia to get drier, and California to also get wetter. But in addition to these effects that surround the Pacific Ocean, we also see that El Nino can affect places all around the globe, such as South Asia, Africa, and Central Asia as well. So understanding El Nino and understanding these patterns are really important for our climate system. Here are two snippets of news articles that I'd like to share that really highlight that. So sometimes this El Nino pattern of drying and wetting can be so extreme that it can cause wildfires in Australia or flash flooding in California. So global warming, El Nino, these are just two of the aspects of the climate systems that scientists like myself are interested in. And there's actually a lot of ways to study this. We can use observations of our planet directly, such as satellites that we send up into space, or floats that we deploy into the oceans from research cruises. We can use complex models of our climate systems themselves. So we can set up our climate system within a supercomputer, such as the one shown here in this massive warehouse, and try to understand using math and numerical models how the climate will change. And finally, one thing that we can do is actually rely on natural archives of climate in the world ourselves, such as trees and corals. And these are the aspects of the climate science that I'm most excited about. So using the world around us and using these natural archives, it's called paleoclimate. And paleo just means really old. And you might be wondering, well, how can trees and corals tell us anything about the climate? Well, the crazy thing is that both of these archives actually create something called annual bands. So every year they grow another layer, and we can actually process and extract these layers and analyze them to understand how climate changed in the past. What's really exciting about these paleoclimate archives is that they can give us an insight into the past way beyond what our instruments are able to measure. There are also other paleoclimate archives, such as sediment cores, that give us insights into the deep time of the Earth's climate. And this here is a picture of Fatima with another graduate student at MIT sampling some of these sediment cores. And so I'd like to conclude by saying that climate science comes in many forms and fashions. You can be a climate scientist like myself that spends most of their time working with numerical models and analyzing data that scientists process. You can be a climate scientist that goes out into the field and actually collects some of these paleoclimate archives. Here's a picture of another grad student at MIT, Ben Tiger. He's here in a cave in Mexico and actually analyzing stalagmite records to understand climate in the past there. Here's another picture of Maria. She's another graduate student at MIT, and she's scuba diving to tropical reefs in the Caribbean and processing coral reef samples there. And you can also be a climate scientist that interacts with policymakers and politicians as well. So here is another picture of a former graduate student in my lab working with the Environmental Defense Fund. And so thank you all for listening to my talk, and I'd like to answer any questions that you might have.
Thank you so much, Shawn. So we got some great questions in the Q&A, but just to kick us off, I wonder if you could reiterate for us, what makes you tick about all of this? Why climate science? A lot of the tools you've described today can be used to study a plethora of different things. So why climate science? What makes you passionate about it?
Yeah, that's a really great question. I think to answer that question, I might be best to really dig into how I became a grad student here. And so I actually came into climate science when I was in college, actually as a chemistry major. So I didn't actually even start as a climate scientist or a geologist or earth scientist. And I found a science course in the geology department that sounded really cool. It was a climate science course that also applied many of the skills that I learned in chemistry to understanding the world around me. And I thought that was great. So I took that and got more involved with that. And I think that that's what makes it really exciting for me is that climate science really draws on a lot of different disciplines. You can be a scientist that is really analytical and works great in a lab. You can be a scientist that is a great mathematician and works with models or works with theory and all sorts in between. And so what makes it great is that it's interdisciplinary. It really involves multiple types of individuals, and it really addresses questions that I think are really exciting and important for us.
Right. And I mean, climate affects everyone, right? So it's our jobs as earth scientists to try to understand this planet we live on and how it affects us.
Hmm.
And that actually brings me to a really great question from Parth. And Parth is wondering, in climate science, you gave us this really great overview of all the different things people do to study past climate, and including me and my research. But why wind? Of all the things you could have studied, Parth wants to know what brought you to wind specifically. Why did you choose this particular topic?
Yeah, that's a great question, Parth. So wind, I think, is really exciting for me for several reasons. One, I think because it's actually very much the driver of a lot of these other changes that we see. So the animation that I showed, for example, when the trade winds weaken, the water temperatures actually change. And that has a big impact on climate in the Pacific Ocean, for example. Wind patterns can also affect the transfer of moisture and rain to different parts of the world. And so that's why it's an important driver of precipitation and understanding droughts. And so I'd like to say that, wind is just a way that different things on our planet move around. And I think that's really exciting and really fun. And also, I just think there's some really beautiful animations that you can see with the wind fields and the vectors and everything. So yeah, some of that too.
No, that's really cool. And you even showed us a couple of those where you're seeing the intensity of temperature change, or you're seeing
Hmm.
those wind currents. And I think that's so fascinating because, of course, we can't really see wind, we can feel it.
Hmm. Hmm.
But to know that this is happening all around our planet on so many different scales, and that it profoundly affects the life below it is really quite stunning. And that leads me to another question from a Nord Anglia student. You've kind of mentioned temperature a few times. How are temperature and wind linked?
Yeah, that's a really great question. So they're linked in a few ways. First off, you can think of wind and temperature being related in the same way as, being inside a room on a hot, sunny day and turning on the fan. The wind can blow the hot air that is sort of sitting around you in your room away, and that can cool you down. And so wind is important for transferring heat from one place to another, and that affects the temperature of the air. Another more interesting way that wind can interact with temperatures is over the ocean. So I showed that over the Pacific Ocean, for example, when these trade winds weaken, the water temperature warms. Not only is that due to the reduction in the amount of warm water that you pile up, but also affects the amount of cold water that you bring from the deep ocean. And so there is this effect of upwelling of deep ocean waters that is actually related to this. So yeah, there's a lot of different levels to it.
Got it. And we have a good follow-up question to that. Just speaking about the trade winds, which you're studying specifically, we have a question from Ashwarya, and Ashwarya is wondering what would happen if the trade winds disappeared completely? And has that ever happened before?
Ashwarya, that's a really cool question. So the trade winds are actually there for a couple, they're actually there for a couple reasons. First, they're actually related to the rotation of the Earth, which is kind of a crazy concept. But the trade winds blow from east to west because the Earth is constantly spinning. And so if the trade winds were to disappear, that would probably be related with a change in how our Earth rotates. And, as far as I know, in our most recent history, the Earth is constantly rotating. Although some scientists do believe that in the far future, as our solar system changes, that the rotation of the Earth might slow down. And so there is potential changes to the trade winds associated with that, perhaps. So yeah, I hope that answers your question.
Yeah, and of course that I mean, it just sounds like you have to think of so many different factors, and what affects, the physics of our planet, which ultimately affects us because you mentioned it yourself. Those were trade routes, and I know a lot of boats kind of rely on that push for the wind. When you don't have that, perhaps you have to use more energy to get across. So I think that could be really important.
Hmm.
And so I'm wondering, we have a follow-up question from Twisha, and Twisha is wondering, what are you currently researching in wind? What specifically about the trade winds? And has this led you to think of, solutions for some of the climate change problems we've faced?
Yeah, that's a really great question. So thanks, Risha. I think so. The example that I gave of an El Nino event and of this trade winds relaxing or reversing and the change in temperatures, we have a really good understanding of how that occurs um, on a year-to-year timescale. So from one year, we have a big El Nino event. The next year, maybe not so much. So climate scientists are actually really interested in, well, what about decade to decade? So the next 10 years, the next 50 years. Some scientists are interested in something like El Nino, but happening on a much longer time scales. So could the next 50 years have trade winds that are even stronger than the last 50 years? And to understand that, well, we don't have observations for the last 100 years or so. And that's why we need paleoclimate to ask these kinds of questions. Are the trade winds changing on these longer time scales? And how does that affect our society in the next 100 years, in the next 200 years? So, I think that is sort of a set of questions that I'm particularly interested in. So, yeah.
Yeah, I mean, there's always more to explore, more to think about. And you're right, it is really difficult to have records of winds. What we have in the geological record is really preserved we preserve the impacts of winds. So you're getting this information really indirectly. And I think that's incredibly challenging and
Hmm.
complex. And that leads me to a really great question from another Nord Anglia student. And Pallavi's asking, how long have these major wind patterns been around on Earth? And when was the last time you think they majorly changed? What factors affect that?
Yeah, that's a really good question. Um, I think that these wind patterns, the ones that I've studied, have been around for a long time, but they have changed in the geologic history quite a lot. For example, some scientists have thought that during the last glacial period, so 25,000 years ago, back when there was a lot of ice on our planet, so the last ice age. So imagine woolly mammoths and saber-toothed tigers, that the wind patterns on Earth were actually really different and that they were actually a lot weaker than they are today. And scientists aren't really sure why that is the case. And that's something that we're really interested in. But as you can imagine, even with paleoclimate, studying something that happened 25,000 years ago is pretty challenging. And like you said, Fatima, we don't really have these direct measures of wind. We only have these proxies of their impacts. And so that's another time period in which wind patterns may have been very different.
That that makes a lot of sense, and that is totally intriguing. And I don't think I realized that. So that's really cool. And that kind of leads me. You mentioned woolly mammoths and saber-toothed tigers, and that brings me to a question about the impacts on land. So you gave us this incredible example of how, just like us, fish have these preferences in temperature, and when the oceans change temperature, that's going to be really difficult for them. They don't have very many places to go. How does this all affect animals on land, or like us on land? Could you help us kind of clarify how this all connects back to the land?
Yeah, yeah, for sure. So yeah, I gave a few examples about climate change and how that affects these other animals and plants. But obviously, it affects us humans as well. So maybe one of the biggest ways that it affects us is how it impacts our water resources. So, for example, when you turn on the water on your tap, or when you go to the store to buy bottles of water, that's water that comes from a reservoir or some source of water, maybe a stream that's being purified through a system. And that amount of water that's in that reservoir is actually very directly linked to the wind patterns, to the rainfall in the climate system. And so some periods of time in Earth's history, um, if these wind patterns change a lot, then the amount of water that we have for us to drink actually changes. And that can have big effects on us. And so that's just one way among the many that these climate change and El Nino patterns can affect us as humans.
Wow, no, that I think that makes sense. And given that we're talking about El Nino, I wonder if you could really briefly review that for us one more time. And we have questions from a few students in the chat from North England. They're wondering, what is La Nina? Because I think they've heard that term as well. So could you tell us
Yeah,
what both of these two things are and maybe what we're experiencing right now on the on our planet?
yeah. So I didn't talk too much in detail about the actual terms El Nino or La Nina. But right, so in Spanish, these means the boy or the girl. And the reason they're called that is they were first discovered by Peruvian fishermen. And because their effects were most strongly felt off the coast of Peru and South America countries. And you sort of saw that warming over the Pacific Ocean, and that actually peaks. That's actually strongest during wintertime, during near Christmas time, actually. And so when these fishermen were out there fishing, these warm waters would actually affect how much fish they were able to catch. And they would have, this impact would be felt strongest around Christmas time. And so they called this event El Nino because they're referring to the Christ child. And that's why it's called that. La Nina is the opposite of an El Nino. So instead of the trade winds weakening, they actually strengthen. And that actually means it's even cooler on the eastern part of the Pacific and even warmer on the west. And that has its own suite of other impacts that it has on climate. But yeah, I hope that helps give some context for why it's called El Nino and La Nina.
Yeah, so these are these, broad like climate phenomena that, do impact all of us and impact our weather and are associated with different kinds of seasons and experiences. And so how do scientists know which one is going to happen? Are we still asking, Peruvian fishermen? How do we know which is which?
Yeah, that's a really good question. So most of the time now, what we use to define an El Nino or La Nina are actually we have an index, we have a metric for what phase our climate is in, and that's mostly by looking at the sea surface temperatures in that Pacific Ocean. So that blob that I showed in the animation off the coast. Most of the time we do is actually we use our measurements from satellites, from ships, and we see, well, how warm is the water there and how cool is the water there? Is it warmer than usual? If so, scientists will declare we're in an El Nino year. If it's cooler than usual, scientists will say we're in a La Nina year. And right now, if you check the weather stations and if you check the satellites, we're currently in an El Nino year. And this is following 3 years of La Ninas for the past 3 years. And so it's been a big change for us.
Wow. Okay. And so to follow up on that, so you kind of talked about um, deciding which year it is depending on whether that those temperatures you're observing are a little warmer than normal or cooler than normal.
Mhm.
How do we use that information to help other people? Can we make predictions about wind to help protect humans, maybe fishermen from the impacts of these winds?
Yeah, that's a really great question. Um, and so the answer is yes, I think we definitely can. There's a lot of scientists working round the clock to try and understand what the impacts of these changes could be. And not only that, but maybe sort of getting at one of your previous questions is, can we predict and can we sort of forecast whether it'll be an El Nino or La Nina? And that's something climate scientists are very interested in. Unfortunately, it's actually quite hard to give a forecast beyond a few months. The winds over the Pacific Ocean, I showed this cool animation of them being very smooth and everything. And sometimes they're like that, but other times they're a lot messier, and it becomes a lot harder to predict what's going to happen. And we try and use the winds over the Pacific to try and predict whether the next year will be El Nino or La Nina. And sometimes it works out, and sometimes it doesn't. And we're sort of still understanding why that's the case. And I hope that me and as well as other future scientists can try and address some of these questions so that we can predict these changes and better prepare for them.
Absolutely. And now I want to zoom out a bit and ask kind of a few questions about you, Shawn, and your background in all of this. And we have a question from Adia, and Adia's wondering, Shawn, do you have a role model? And if yes, who is it and why?
Oh, wow. That is a great question. I would say that my role model is probably my dad. He is also a scientist. He is a veterinary scientist, a microbiologist, and he also has his PhD. And I think he really inspired me to pursue a career in sciences. Uh, Even as a little kid, he would always introduce me to new scientific concepts and always encourage me to uh, explore different avenues of science and be excited about what I did. And in college, he always encouraged me to pursue my passions and pursue whatever it is that excited me. And I think that that has been really instrumental for me in being the scientist that I am today.
That is totally wonderful. That's really cool. Okay, so following up on that, we have a question from a Nord Anglia student who's wondering, what are some of the challenges you face in your work day to day, and how do you overcome those challenges? I think you kind of hinted that, the data isn't always as beautiful and mesmerizing as it was in those videos you showed us. Sometimes it's really messy, and that might be one of those challenges. But how do you deal with challenges in studying something this complex?
Yeah, that's a great question. So as I alluded to in my talk, I work a lot with climate models that try and simulate and predict what our system looks like. And sometimes these models predict changes that are consistent with what I think, and it's really great and it works out really well. Sometimes the models don't give the results that I thought they would, and it can be frustrating. Sometimes this can be because I made a mistake in coding out the program. Sometimes there's just noise in the climate system that we don't fully understand. And one way that I think really helps for overcoming some of these day-to-day challenges is really just reaching out to other students and other scientists. I think that sometimes having a new perspective on things just really helps me. So I'll stand up, I'll take a walk, and I'll maybe all it takes is just me explaining the problem that I have to another fellow grad student. And they'll just say, well, have you tried looking at this? Or have you tried this other method? And a lot of times that actually works. So yeah, I think what really excites me about climate science and earth sciences is that it's so interdisciplinary and it's so collaborative. We're all on the same team. We're all trying to understand this climate system. And that I think really makes it worth it.
I really like that you said that, Shawn, and I'll let our listeners today and the students today on the call in on a little secret. But Shawn and I work on the same building, so if I have a question about wind or I have a paleoclimate question, I'm going to walk right over to his office and ask him. And I think that's one of the really exciting things about our field, like you say, Shawn, and just it's really exciting to be at MIT and to have people with such incredible, diverse sets of expertise around every day. And that also brings us to another question, Shawn. How did you get to MIT? How did you get to the Woods Hole Oceanographic Institute?
Yeah, so I feel very fortunate to be here. I feel really lucky to be among such great scientists. My journey here really started with my undergraduate advisor, Bob Anderson. So he was an oceanographer, and he was the teacher of a class that really inspired me to pursue climate sciences. And he basically, when I graduated college, I wasn't sure what it is that I wanted to do. And I was thinking that maybe I might apply to grad school and really study climate sciences. And he really encouraged that, and he allowed me to stay on as a research assistant, as a lab technician, for 1 year in his lab. And it was there in that lab that I really developed some great skills for being a climate scientist. And I got connected with other scientists at MIT and at Woods Hole, and that led me here. And so I feel like I felt really fortunate that I had great mentors and advisors along the way that helped guide my career. And that's how I got here to where I am today.
That's fantastic. Yes, we all need those role models, mentors, and advisors to get us and keep us on the right track, and to push us to do really exciting things. And now, another question about your day to day, Shawn. Do you go into the field as part of your work? Like, are you ever, measuring wind somehow out and about in the open, or is most of your work on the computer? What does a typical research experience look like for you?
Yeah. So I actually used to be in the lab a lot. I used to actually be the scientist that measures some of these paleoclimate archives that I talked about that Fatima works with. But I've now transitioned to working mostly in the computer realm, and I mostly do modeling. So my day-to-day usually involves coming into the office and starting up all my programs and visualizing some of these patterns that I showed, and trying to understand and make sense of them. Sometimes I'll go to the whiteboard and try and diagram things out or write equations out. And yeah, it sounds maybe not as exciting as going out to the field. Sometimes I'm jealous of my friends that get to go to the Caribbean and swim in the tropics. But I really enjoy what I do. I really enjoy being able to work with these large data and think of all these changes on such big scales. And what's exciting about that is that I work a lot with models and with math and physics, but I actually was not great at math in middle school and high school. I was actually really anxious about my math classes, and it wasn't until much later that I actually became to really be excited about statistics and math and physics. So for anyone out there that is interested in climate science, interested in some of this stuff, but you're afraid that you don't have the skills, I would say just, keep at it. And if that's something you're passionate about, things will develop and skills will develop.
No, I really like that. And that leads into, unfortunately, what's going to be our last question today. We have so many amazing questions in the chat, but not enough time to ask all of them. But I want to leave you with a question from Anya, because I think what you said just leads so nicely into this. Anya's wondering, what advice do you have for us if we choose the same path as you in the future? She says that she's really inspired by your talk, and maybe, she wants to, we have some future climate scientists on this call, Anya included, perhaps.
Absolutely. Thanks, Anya, for the great question. I think that my advice to you would be to really not be afraid to explore new things. I think do what it is that you're passionate about. So if it's earth sciences, if it's climate science, then really get involved. Um, I remember, when I was in middle school and high school, I really liked going to the public library and just really, reading and learning about some of these things just on my free time, just for fun. And that was really great and inspiring me. So whatever it is that you think inspires you to really follow that passion, that's the first thing. Second thing I would say is, as you get older, to find those right mentors, to find the role models and find the individuals that are older that can help you develop and nurture those passions. And the third thing I would say is don't be afraid to fail. I was so afraid of doing poorly on my math exams or something like that, I think that I really held myself back sometimes. And so don't be afraid of making mistakes and don't be afraid of asking for help and developing your skills and becoming better at all of these things. And so, yeah, I hope that helps. And I know that there's some future scientists, future climate scientists out there on this call. And thanks for coming.
Wonderful. Well, thank you so much, Shawn. And I hope everyone will join us again next month for an MIT abstract on what makes bacteria sick. That's going to be really interesting. And with that, I'd like to thank all the students today for asking such wonderful, wonderful questions. I'd like to thank the MIT Nord Anglia Education Collaboration for making this series possible. And lastly, I'd love to thank Shawn. Thank you so much, Shawn, for joining us today, for sharing with us your expertise, and for teaching us about wind and just how incredibly impactful it is in this really complicated climate system we have. Thank you, Shawn.
Thank you so much. Thanks, Fatima. And thanks everyone for asking great questions.
Wonderful. Okay, well, we'll see you all next time. Bye, Shawn.
Bye.